Thank you.
Thank you. So we're ready to start this second module on optimal power flow. Last week, we saw how to pose and solve an optimal power flow, at least with some simplified techniques. But we have not addressed an important element, which is handling uncertainty. Last week, we did as if everything was known in advance: the generation, the weather conditions, the load consumptions. This week, we will see the techniques that allow us to handle in the optimal power flow some uncertainties. So keywords will be removal of quantifiers, stochastic optimization, and robust optimization. Let us start with some technical issues which have to do with how we manipulate and solve an optimization problem in which we have what I call quantifiers, which are here to handle uncertainty. What is a quantifier? A quantifier is a symbol like this one here, which means for all. There's another one which is there exists. So here is a problem. Take it as an abstract optimization problem where I am minimizing some function of U1 and U2 over U1, U2. So when we pose an optimization problem, it's always important to know exactly what are the optimization variables. Here, the optimization variables are the U's. The objective function depends on the U's. And then I have constraints on U. I write them in an abstract form here. And then I have a special form of constraint which says, for all number D1 such that D1 is between 4 and 5 and U1 plus 2 U2 minus 3 D1 is less than or equal to 10, then this inequalities must be satisfied. So what does that mean here? It means that we are imposing on U1, U2 some constraints that depend on a continuous variable D1 here. D1 is very frequently called a disturbance, and in our cases, it represents the uncertain parts of what we're modeling here. For example, this could be the difference between the forecast and the actual load consumption or PV generation here. So here we're expressing that the constraints must be true, whatever the value of the disturbance. For example, for a grid, we want that the voltages are within nominal bounds, whatever the uncertainty realization will be for PV production. Note here that D1 is a dummy variable, is not an optimization variable. It's just something that is used to express constraints. It happens that D1 is a continuous variable, so we cannot simply treat it as a supplementary index. But it's not an optimization variable in the sense that when I ask MATLAB to solve for this problem, it will return an optimal U1 and U2 and not an optimal D1. Let me ask the following two questions. If I consider those constraints here, remember those are constraints on U1 and U2 that contain a dummy variable D1. If I want to remove D1, for example, an oracle proposes to me that this is equivalent to U1 plus 2 U2 less than or equal to 22. Here's another formulation. Is any of these formulations true? I close the poll in a few seconds. Closing. And the majority says A, which is true, but B is also true. So the correct answer is C. Why is that? Well, the constraint says that for all D1 that are in this set of values for D1, this expression that has both U and D is less than something here. Now, saying that an expression is less than something for all values of D1 is the same as saying that this expression is less than the minimum. So here I can, in this inequality, I can separate the U and the D. This is equivalent to U1 plus 2U2, which are my optimization variables, less than 10 plus 3D1, which contains only the disturbances here. And saying that U1 plus U2 is less than this for any value means that it is less than the minimum. So that's the trick. That's a very important trick. We will see other similar tricks, but that's very important tricks that you need to master to be able to handle optimization problems that have uncertainty. So here, that means that the constraint here is equivalent to statement A, U1 plus 2U2 is less than this, with this minimum of this expression over all D1. You realize here that you have an optimization problem on the right. We have the optimal value of an optimization problem here. So the first thing that will happen when we have uncertainty, therefore quantifies and constraints, we will have induced optimization problems to get rid of the uncertainty, which is exactly what we have done here. Now, in this specific case, I can solve this optimization problem very easily, finding the minimum of 10 plus 3D when D is between 4 and 5, where the minimum is reached when D is equal to 4, which gives the value of 22. So condition B is equivalent here. You see that when we have condition B, the value D1 has disappeared, which makes sense because D1 was a dummy variable. So let's see another type of quantifier and constraints. The other quantifier is this one here, the inverted E means there exists. So I have similar things here, except now I want to allow all the values of U1 and U2 for which there is at least one value of D that satisfies that here. So same comment as before, D is a dummy variable and the problem, the optimization should return an optimal value of U1 and U2. What do you think? What can we say? Same question as a few minutes ago. Which form, if any, is equivalent to the problem that we had before, which is the same as before, except now we have there exists instead of for all. I close the poll in a second. The majority says C, which is the correct answer here too. The difference is that we require that there is some D. So the same trick, we can separate the U and the D and say U1 plus 2U2 is less than 10 plus 3D1 for at least one D1. And then we have the general pattern that says that an expression is less than f of D1 for at least some D1. This is equivalent to saying that the expression is less than or equal to the max of D1 here. So that gives the first formulation, U1 plus 2U2 is less than this max. And here, same as before, the max is easy to compute, is obtained for D1 equal to 5, and that gives us the second constraint here. Therefore, we see that the problem is equivalent to a form where we have removed the disturbance variables and the quantifiers here. Here's yet another form of the problem, which we will also often find. Here, I have the same statement, except I have not put a quantifier. I've put D1 in the variables here. but the D1 does not appear in the optimization function here. Again, it's important to, when you write an optimization problem, to write what the optimization variables are. Sometimes we're a bit sloppy and we don't do it. We say, minimize this expression with those constraints, and then we don't know what is a parameter. For example, there could be, instead of 5 here, I could have a parameter, which is a fixed thing, or like D1, which is appearing here, not as a parameter, but an optimization variable. So when we write it as an optimization variable, that means we want to find an optimal value of U1, U2, but also D1 that minimizes this, subject to all those constraints being satisfied. So there is a third form that's very close to the two forms we saw before, and it will be important to relate it to those previous forms. To test your ability to relate it, here are 3 versions of a problem. The problem, the one that I just showed before, then the 2 other problems that we saw on the 2 previous slides here. If I solve P3, is it giving a solution of P2 or of P1 or none of them? Is that unrelated? What do you think? I close the poll in a few seconds. And the majority says B, which is the correct answer. Here it's very important to have clear views on this topic, because transforming the problem into something where we have removed a variable or introduced a quantifier is something that MATLAB will not do for you. That's something that you have to write. Solving the problem is, solvers will do it for you. But writing the problem or transforming the problem by changing the nature of the problem that's something that you have to be aware of what is happening. Here, P3, what are we doing in P3? In P3, we say we want to find U1 and U2 and D1 that satisfy all those constraints and minimize this variable. Then, as we will see in a second, this is equivalent to the following one, where here we say I want to find U1 and U2, but such that those constraints are satisfied. Now, if the constraints are satisfied, that means there exists a D1 that satisfies the constraint. So the only difference between P2 and P3 is that in P3, we care about the value of the optimal D1, whereas in P2, that's a disturbance or a nuisance variable that we don't care about. We don't ask MATLAB to return the value here. Here, but they are equivalent here. So if we solve P3, we'll find an optimal D1 star, and the optimal D1 star is such that U1, U2 star satisfies P2. There exists a D1, it is exactly the D1 star, and vice versa. In contrast, for P1, then it is not at all the same as P2 or P3. Because in P1, we're saying those constraints must be true for any D1. Why do we do that? Typically because we are playing a game here where we have an opponent. The opponent in the language of game theory, in the language of smart grid, it would be nature. We have a disturbance, but we can view things as we are trying to set values of generators or control parameters in our grid. And there is something that's playing against us, which is nature, whether the forecast of weather will be exactly what we said or not. That does not depend on us, but on an opponent that plays independent of us. And we don't know what this play what this player will do. So D1 will be chosen by someone else, and we have to choose something, U1, U2, not knowing D1 here. In the other two problems, we choose D1 as well. So here we choose U1, U2, and D1. So that means we have full control over D1 here. In that case, D1 would not be a disturbance, but perhaps a second phase of the optimization, where first we choose a number of parameters, then we observe the results, and then we might choose another one. But in this case, we choose U1, U2, and D1. Here, we don't choose it. So there's a radical difference between P1 and P2, but P2 and P3 are exactly the same here. In fact, this is quite general. So I call this supplementary variables and constraints. Whenever we have a problem of the form constraints with quantifier of the form there exists, it is the same as adding all the variables that are quantified with there exists into the optimization variables. So if I have minimize phi of u, so the objective function depends only on u, but the constraint depends on the existence of a dummy variable d, it's the same as putting d as an optimization variable and not changing anything. We keep the same constraints. D must be in this set of feasible values of d. The constraints c of u and d must hold here, and the other constraints that don't involve d must hold. More exactly, of course, the two problems are not exactly the same, because here we have optimization variables that are u, whereas here they're u and d. So formally, they are not the same, but they are the same in the sense that the optimal values are the same, are equal. And if I have solved A, I have an optimal value u star. Therefore, for this u star, there exists a d, which I call d star, that satisfies the constraint that d is in the set d, and the constraints written here is also satisfied. So there exists a d star such that u star d star is an optimal solution of B. And vice versa. If I have an optimal solution of B, then the u star is an optimal solution of A. So apart from this change of whether a variable is a dummy variable or is an optimization variable, it is the same. So take home message. First, if we have quantifiers in the form for all d expression less than f of d, where expression does not depend on d, this is equivalent to saying the expression is less than or equal to the minimum. If we have there exists, it's equivalent to less than or equal to the maximum. Of course, if we had larger than, then we have similar results with min and max that are reverted. Which means that concretely, we can remove those quantifiers, which are embarrassing, by introducing supplementary optimization problems here. And the other thing is that there's a fundamental difference between there exists and for all. There exists means somebody, us possibly, can choose a value, and therefore, if there is a there exists in an optimization variable, in the constraint here, we can simply add this variable to the set of optimization variables. So it's at the expense of increasing the size of the problem. Now, those two problems are different in size. As we have seen in the examples in the quiz a few minutes ago, I can translate this constraint by a constraint that does not have d, or I can add it. If I add it, I increase the size of my problem. So it's not exactly equivalent in terms of complexity, but it is equivalent in the sense of what we are mathematically computing. Well, so that's the preliminary mathematics that is very simple, often overlooked, but it's important to have those things clear, because now in the rest of this lecture, and probably in other contexts when you will be doing realistic optimization problem where you will have uncertainty, you will be constantly confronted with that here. Here's an example, a larger scale example of a problem P. That's a big problem P here. We'll see it in a second. It should look familiar to you. It's the same problems we had last week when we were optimizing the grid generator set points, with the difference here that I'm assuming that the loads are within intervals. So we don't know what the loads will be, but we think we have a good forecast in terms of prediction intervals here. And the rest are the equations of the grid. You recognize here the DC approximation of the grid here. So we have the power flows on the lines, the generator set points here, and here the generator set point at the slack bus. We'll come back to that in a few more minutes, That's my problem, my original problem here. I want to minimize this, and here I wrote it in this form. Which of the forms that I'm writing here, A and B, is equivalent to problem B? I close the poll. And the correct answer is, of course, A. Here, we have put the disturbances as optimization variables, here, the loads, which means that, in fact, we are solving problem A. Means there exist disturbances that satisfy those constraints. I said this is a problem we have when we have uncertainty about the loads, but I was misleading. This is incorrect. By doing that, we're choosing the disturbance, we're choosing the load. So when we solve this, we say, well, we are choosing the loads. The real thing we probably want to solve is problem B. We say, I don't know what the loads will be, but I need to decide now on the generator set point. So whatever the load values, all my constraints should be satisfied here. So the bad news is that, well, the good news is solving A is the same as P. The other good news is that now you are able to make the difference. But the next question is, how do we solve a problem such as B here? Well, for this specific case, problem B has the property that the constraints that involve the optimization variable, so let me look here, G2, G3, and the constraints that involve the disturbances are separated, exactly like we did in the quiz a minute ago. If I look at one of those here, there are two inequations, one here, one there. If I look at this inequation here, I can put all the control variables, G2, G3 on one part, and all the disturbances on the other part. So we have a case of what we use, of what I call separable constraints here. So in general, I formulate this in this generic form. So I put it in this generic form so that once we've understood the method, we can use this cheat sheet here to do it once for all. So I have to minimize a function of my control variables U, where I have a number of constraints of U, and then some constraints that involve a disturbance variable D, where the disturbance variable joint constraints between the control and the disturbance variables can be separated. There is a term in U and a term in D here. So if I have this, we can do systematically what we did in the quiz. I can put all the disturbance on one side and all the disturbance on one side and all the controls on the other side. That gives me this equation here. And then I use the trick I said before. We impose, that's a constraint on U. Remember, D is a dummy variable. So this must be true for all values of D. And this is equivalent to saying this is true for the minimum of the values of D. So that means I have to solve for each of these inequalities here. I have to solve one optimization problem, which consists in minimizing gamma minus BD, which is this term here. Once I have, so if in this simple case, this is a linear problem, so it can easily be solved numerically by MATLAB or LPsolve, whatever. I call H the optimal value For every J, there is a different one. So if I have capital J constraints, I have capital J problems to solve, then I call Hj the result. Then I can change this inequality, which is here, by that one, which has now no disturbance variable. So at the expense of solving one optimization problem by robust constraint, I can get rid of the robust constraint here, which is what I'm writing here in summary. This problem here with capital J robust, I call them robust constraint. Those are constraints that must be true for all values of the disturbance. I solve the optimization problem and I can replace every robust constraint by this inequality here. So that's one technique, which is, of course, requiring to solve a number of additional optimization problems. But solving many small optimization problems is typically not an issue. The complexity of optimization is a problem when the size of the optimization problem itself grows. Voila. So we are finished with the mathematical prerequisites. Now we can see how we will apply this to our grid problem. For that, we need to discuss a number of other things because there is not one single framework. There are many subtle variations that are dictated by the capacity of solving numerically with reasonable complexity the resulting problems. As I mentioned before, this is motivated by uncertainty in some of the environment variables. For example, in this very small, simple grid that we saw last week, instead of assuming that the load consumptions L1, L2, L3 are fixed, I can assume that they are predicted with some uncertainty. This is typically fairly easy to do, at least in electrical grids for load consumptions, because there are historical data, and then there are very sophisticated forecasting systems for predicting deviations from forecasts, from a standard forecast, for example, due to an event, whether it's a weekend or whether the weather is fine or not. So that gives us forecasts that can be more or less good, and how good they are is reflected in the width of this uncertainty band here. Here, I'm assuming we have 10% uncertainty on L1, L2, and a bit less on L3 here, which is typically the case. The larger the loads, typically the less the uncertainty is. This is here due to load consumption. Of course, there is always uncertainty about the load consumption because it depends on human activity, but it's very, very predictable. Net load today is the algebraic sum of load consumption and minus PV generation, because we have solar generation in many, many places here. Here, the forecast techniques is different, and the uncertainty is usually a bit larger because weather is a bit less foreseeable than human activity. And that may change the prediction intervals, but doesn't change the methodology here. So how can we return to the problem we had before? I'm assuming here I need to compute the set points of G1, G2, G3, but now assuming there is some uncertainty. So what can I do? The first thing here is that, of course, I cannot simply take the problem I had before, because the problem I had before had an objective function here and constraints, but we see that the constraints have the uncertain variable. So it's not possible to find G1, G2, G3, theta 1, theta 2, and theta 3 that satisfy those constraints for all values of L1, L2, L3. So for every value of L1, L2, L3, there is an OPF, there is an optimal solution, and which one should we choose? So let's discuss how we can go over this conceptual issue here. First, to simplify here, let's assume that G1 is the slack bus. That means that the sum of the power consumed and generated in this grid is cancelled by G1. So we need to control only G2 and G3, because if nature controls L1, L2, and L3, if we control G2 and G3, then G1 will follow here. So our control variables are G2, G3. The disturbances now are L1, L2, L3 here. Now, the first issue we need to sort out is what is our cost here? cost of generation is dependent on G1, G2, G3. Of course, G2, G3 are our choices, but G1 is affected by both our choices and L1, L2, L3. Because if I use the DC approximation, there is this algebraic equality here that gives G1 as a function of the control and the disturbance here. So we cannot take as cost function simply this here. We need to do something else. What should we minimize is the first question. And second, the constraints of the grid must be satisfied for all values of the disturbances here. There are multiple ways to answer those two questions. The first way is called stochastic optimization. In stochastic optimization, we assume that the disturbance is random and has a certain distribution that we may approximately know. So I repeat the framework of this problem. It's very important for all those types of problems to know what the framework is. What is a control variable, what is a disturbance, what is known in advance, or what is not known a posteriori. So here we have to choose some control parameter. We have to choose it in advance here. The control parameters are G2, G3. Nature will choose some random disturbance after our choice of U here. Then as a result of this, there will be a system state. That will be the system of the grid, which is a function of our preliminary choice and of the posterior choices by nature here. And we want that the system state is feasible, and it must be feasible for any value of the disturbance here. Now, what is the state? Well, the state here in our case is, for example, the state of the electrical grid here. The cost that we pay for this, so we choose U, nature chooses D, and then we pay. We pay as a function of U and the state, therefore, indirectly, we pay as a function of U and the disturbance chosen by nature. So you see, this is exactly a game. There are two players, and I am the player. I'm choosing the control. Nature plays after me, and I have no control on what nature will play. And I pay for the result of my preliminary decision and the choices of the adversary, which is in this case nature. Although in a smart grid setting, we should not treat nature as an adversary, but that's the language of game theory. In stochastic optimization, as I said, we assume that the disturbance is a random variable. And in this case, the optimization function is the expected cost here. So we get around the problem of the fact that the cost depends on something that we don't know by saying we take as cost, which I call C bar of U, the expectation over all the possible realization of the random variable D of this cost here that depends on D here. So that's one of the principles of stochastic optimization. So stochastic optimization will replace the unknown cost by its expected value. Therefore, at the end, we have a function of the control variable only, which we call C bar of U. And that is simplifying the problem because we don't have the disturbance here. So one of the design decisions when we cast stochastic OPF, for example, is to know how we will get a handle on C bar of U here. For example, here, if I assume in this very simple case that the costs are linear, so the cost of generation G1 is a constant time G1, then the expected value, because G1, the true G1 is equal to minus G2 plus G3 plus L1 plus L2 plus L3, right? This is the DC power balance equation here. Of course, if we had AC OPF, we would need to add the losses. That would make a nonlinear term, but other than that, the principle would be the same. The expected value of G1, remember, that's expected with respect to L1, L2, L3 being treated as random variables. So I replace L1, L2, L3 by their means. Since all of this is a linear function of the random variable, the expectation of a linear combination is simply the linear combination of the expectation. So G1 bar is minus G2 minus G3, which are my control variables, plus this L1, L2, L3, which are the expected values. So I assume L1, L2, L3 follows some distribution from which I can know the mean value. For example, here, if I assume L1 is between 90 and 110, I could assume different things. I could say, for example, this is a uniform distribution, and the average is the middle, which is exactly 100 and 100 and 500. So L1 bar, L12, L13 are given by 100, 100, and 500. So that gives me a cost function here, which I call C1 of G bar. And as you see, the cost function has only the control variables, which is the first part of stochastic optimization. The second part consists in saying that, well, those variables must be true for all values of L1 and L2 and L3, which means here that the state, as we have seen before, the state which is θ2, θ3, that's the variable that was called X in the generic formulation of a few minutes ago. The state here depends on the disturbance here. So we must have constraints on the power flows here that depend on the state, therefore depends on the disturbance, and must be true for all values of the disturbances here. So the second step of this application of stochastic optimization consists in casting those constraints in a way that is tractable. How do we do it? Well, we do exactly what is in this program here. I express the state X as an explicit function of the control and the disturbance. So I get rid of the unknown state here. Therefore, I will have constraints where I will have only U and D. This is what I'm doing. That's my program. So I apply it here. So the goal, in other words, is to eliminate θ2 and θ3 here when I know G1 and G2 here. So I'll eliminate, I eliminate first the redundant information P1, P2, P3 here by saying that I will solve for this equation as a function of θ2 and θ3 here. So I've eliminated P1, P2. They are given by the simple DC approximation here. And the next state is to eliminate the state. So I need to solve for θ1, θ2, θ3. So θ1 is easy, it's equal to 1. And here I have those equations here. So those are linear equations. We know that they are redundant, they're summed to 0. So I take two of them and I solve them for θ2, θ3, which of course has some complexity, but it's a linear problem to solve here. Therefore, this is what I did here. θ2 is given by those expressions. θ1 is given by this expression. We see that we have the control variable G2, G3, and the disturbance L2, L3 here. Now, the power flow equations that were the flows on the lines. Now, they depend on the θs. The θs, I've expressed them as function of G2, G3, L1, L2, L3. So at the end, I obtain those sets of inequalities here. It's a bit ugly when we look at it in detail, but I hope I've tried to give you a generic framework to do that. The framework consists in eliminating everything except the control and the disturbance. And at the end, what I obtain is two things. I have an objective function, as we have discussed, that contains only the control variables. Here, this compact term here reflects the mean values of L1, L2, L3 here. And second, I have constraints that must be true for all values of L1, L2, L3, but that contain only the G and the L1, the G's and the L's, the control and the disturbance. Here we are lucky that we can separate the control and the disturbances, so we can apply the method we saw before. So we can solve this by solving a number, by applying the method and computing the maximum of optimization problems here. Let's see how we do that. The first constraint, it is, for example, this constraint here. So let's look at this constraint. G1 min is less than minus G2 minus G3 plus L1 plus L2 plus L3. How do we get rid of this? Here I assume G1 min is 0, so that's the constraint I have. How do I get rid of this? Well, I say, by the trick we said before, it's equivalent to saying G2 plus G3 is less than this for all value. Being less than something for all value means you're less than the minimum. So G2 plus G3 is less than the minimum of that here. So I need to solve this optimization problem. I find an optimal value, which is 6.6. So the first constraint is G2 plus G3 is less than 6.6 here. So we see that when we have uncertainty, we have like the equivalent of other constraints that were not at all present in the physical constraints of the system. The physical constraints come from power flow limits, from generation limits. We have seen also in voltage control, they come from voltage limits. But here we have something else which is derived from control from here, a minimum power limit, but that is not a physical quantity that is directly related to a power limit, but has to do with the bounds on the uncertainty here. So this is how I got rid of one of the problems here. So G1 plus G3 less than 6.6. This was the first constraint. If I do that for all the constraints I had before, then this is what I obtain. At the end, I obtain, with considerable work, a problem that is, in fact, much smaller than the original OPF problem. I have only two variables, G2 and G3, and I have a number of constraints here. In some of the constraints, we recognize the physical power constraints, and in the other, we recognize a combination of the physical constraints and the result of robustification, of removing the quantifiers here. So this is the robust problem that we obtain when we have this uncertainty on the loads. Essentially here, what I've added is plus or minus 10 megawatt of uncertainty on L1, L2, and plus or minus 20 megawatt of uncertainty on L3 here. If I change the constraints, if I put more uncertainty, if the loads become more uncertain, then those constraints will change here. The right-hand side, which are not physical quantities, but the combination of physical quantities and the uncertainty bounds, then they change here. This is what I obtain if I add this uncertainty. And here, if you observe what happens here, I have two inequalities that are inconsistent, they're incompatible, which means this problem is infeasible. The constraints cannot be satisfied. There is no value of G2 and G3 that satisfy this because the lower bound here is larger than the upper bound. So that can happen. That typically does not happen a lot when the constraints are exactly derived from physical quantities. But when they are derived from a combination of physical quantities and uncertainties, then this may happen. So you remember last week we talked about what it means for a problem to be infeasible. Well, that does happen. Fortunately, MATLAB and like all LP solvers will recognize when a problem is unfeasible. Here it's easy. I just screen my inequalities and I say, oh, obviously this is not possible. But in reality, you will have hundreds of variables, many inequalities, and it might not be obvious to see that it's unfeasible. Fortunately, linear program solvers do know whether it's infeasible. Here it's infeasible means there's no solution. I cannot run this grid, at least not with this method, because there's too much uncertainty. It's impossible to find set points of G2, G3 that will work for all possible values of the uncertain loads in this range of uncertainty. So if we have such a large uncertainty, we will need to do smarter control, which we will see a bit later today. The smarter controls consist in not just fixing G2 and G3, but we'll talk more about that a bit later here. So if we look at the optimal cost here of the system here, which is plotted on the y-axis, the value we saw last week is the value plotted here for L3 equal to 0. Here I assumed I scale linearly the uncertainty from the value here to that value there. in fact, from 0 to this by scaling it linearly. And I plot here only the value of the uncertainty on L3. So the value of uncertainty of L3 that we saw last week was 0. And the other value we saw in this example was 20, which gives this value here. We see that as we increase the uncertainty, then the cost of the grid increases here. So that's a very important thing to remember. It's obvious if you think about it, but like many obvious things, it's often forgotten. If we have to take control decisions like G2, G3, when there is some uncertainty about the environment, the more uncertainty there is, the more expensive our choices will be. And we see why it is here. We see that as the uncertainty increases, we are forced to give less generation to G2 and more generation to G3, and G3 is the most expensive one. It is because we don't know what is the worst case, and we have to set values of G3 that must work for the worst case. Since the grid is limiting, we may be forced to choose a value of G3, which is not optimal for small values of L3, but is the only one that works here. It's very easy after the fact to say, oh, you had picked this value of G3, that's a very bad idea. If you had been smarter, you had picked a smaller value and your cost would be smaller. It's true, but this is forgetting that we had to take the decision before. So taking a decision ahead of time when there is uncertainty costs something, and it's unfair to come after the fact and say you had to take a better choice. It was not possible because we had to satisfy all the constraints of those uncertain events here. This is why, of course, quantifying uncertainty is important, but also this is why having control laws, control systems that are able to adapt to uncertainty is important to reduce this cost of uncertainty.